All right, let's take a look at introducing the mole. In the warm-up, it says it takes 15 gulps to drink a bottle of water. What information would allow you to calculate how many slurps it would take to drink an identical bottle of water? Well, we need to know the number of slurps per gulp. If 4 slurps is a gulp, how many slurps is it going to take to consume 15 gulps, a 15 gulp drink? Well, if you have 15 gulps, and we can rewrite 4 slurps equals 1 gulp into a fraction, I would put 4 slurps on top over 1 gulp on the bottom, because that would allow me to cancel gulps, and then 15 times 4 would be 60 slurps. Number 3, if 5 slurps equals a gulp, how many gulps would it take to consume a 20 slurp drink? Well, if we start out with 20 slurps and I rewrite 5 slurps equals 1 gulp as a fraction, I would put 5 slurps on the bottom and I would put 1 gulp on the top. So 20 times 1 over 5 would be 4 gulps. So the mole concept, just underneath the warm-up, is a quantity that's equal to the number of atoms in the atomic mass of any element expressed in grams. So let's go back to how much an oxygen atom weighs. An oxygen atom weighs 16 times as much as a hydrogen atom. So we would need 16 grams of oxygen to have the same number of atoms as a gram of hydrogen. If we extend this concept or reasoning to all elements on the periodic table, Fe, for instance, is 55.85, chlorine, 35.45, sodium, 22.99, carbon, 12.01, all of those masses of each element have the same number of atoms. Since the masses are in the same ratios as their individual atomic masses. So this is known as the atomic mass expressed in grams have the same number of atoms for each element, and they called this the mole. And the definition of the mole is very, very useful when we're trying to convert between different units. So the number of things in a mole is referred to as Avogadro's number. And chemists currently estimate that a mole contains 6.022, 14179 times 10 to the 23rd things. So a mole is approximately 6.02 times 10 to the 23rd of anything, just like a dozen is 12. And a mole is an absurdly large number. A mole of peas would cover the Earth's surface with a layer of 200 meters. And it's just a convenient unit for chemists to group atoms and molecules into. It was introduced in the early 1900s by Wilhelm Ostwald. He developed the mole concept as an alternative to the atomic theory because he didn't accept it. And if we take a look at the next page, let's take a look at this quick check here. It says, how is a mole like a dozen? Well, they both represent a number or a quantity of things. B, how is a mole different than a dozen? Well, a dozen is 12 of anything. We technically don't know exactly how many things are in a mole if you go through the reading, but a mole is approximately 6.02 times 10 to the 23rd things. What does a mole of chlorine atoms weigh? If you look at the back of your periodic table at chlorine, 35.45 is the atomic mass of chlorine. We stick a G after it. That's the mass in a mole of chlorine. When you're recording these masses, you record them to the hundredths place. And if you're using the periodic table in the back of your book, I believe they are already recorded to the hundredths place. What mass of sulfur has the same number of atoms that are in a gram of hydrogen? Well, sulfur relative to hydrogen on the periodic table is 32.07 grams. Now, how can we use this concept of a mole for converting between a number of things and moles? Well, if you have to get from moles to a number of things or items, you would use this conversion on the top blue arrow. You would multiply by 6.02 times 10 to the 23rd things over 1 mole. How do you get from a number of items to moles? You would divide by Avogadro's number. So you would multiply it by 1 mole over 6.02 times 10 to the 23rd items. So since a mole equals 6.02 times 10 to the 23rd things, you can rewrite this as a conversion factor. You have 2 different ways to write it, one with the mole on the bottom or the mole on the top, depending upon the unit that you're trying to cancel. So let's go ahead and take a look how this is done. In this sample problem, they want to know how many oxygen atoms are in 3.2 moles of oxygen. So 3.2 moles of oxygen is here. Since moles of oxygen is the unit that you're beginning with, you need to put that on the diagonal so it cancels. You're going to atoms, so it would be up on top. Always include the symbol of what it is that you're using. Don't include the name. Do not write it out as oxygen, just write it as O. And then 6.02 times 10 to the 23rd is on top. You would multiply. In your calculator, this is 3.2 times 6.02 second E 23. Enter. You want to have 2 significant figures in your answer because of the 3.2 having 2 sig figs. That's how you get 1.9 times 10 to the 24th. Now, if we go to the next page, number 1 says, chromium ions are responsible for the beautiful colors of rubies and emeralds. How many chromium ions are in 3.5 moles of chromium ions? So we start with 3.5 moles of chromium ions. You would write that as Cr plus 3. Do not write it out in words as chromium ions. Moles of Cr plus 3 goes on the diagonal because you are trying to cancel this unit. And we are going to chromium ions, so we're going to put that number on top. The number 1 goes next to moles because 1 mole is 6.02 times 10 to the 23rd things. So the 1 goes next to moles, and the 6.02 times 10 to the 23rd goes next to the ions so that these can cancel. So this would be 3.5 times 6.02, second E 23, enter. And this would give you 2.1 times 10 to the 24th chromium ions. You want 2 sig figs in that answer because this number 1 is exact. For number 2, you've got 30 moles of water. We want to convert that to molecules. So you're going to take your 30 moles of water. On the diagonal, you write moles of water. On top, you write molecules of water. You can't abbreviate molecules. You're going to put the number 1 next to moles and the 6.02 times 10 to the 23rd next to molecules. In your calculator, this is 30.0 times 6.02 second E 23. This will be 1.81 times 10 to the 25th molecules of H2O. For number 3, how many atoms are in 0.023 moles of sodium? Moles of sodium is on the diagonal, and you're going to put atoms of sodium on top. The number 1 goes next to moles, and the 6.02 times 10 to the 23rd goes next to atoms. So this is 0.023 times 6.02 second E 23. you're going to need 2 sig figs in your answer. It's 1.4 times 10 to the 22nd atoms of sodium. Okay? Now, what if I am going to convert the other way? So this time I was converting from moles to number of things. But what if I want to convert a number of things to moles? So let's take a look at the sample problem before we do that. I have 7.3 times 10 to the 24th carbon monoxide molecules. We want to know how many moles that is. So you put the number and the unit that you're given here, molecules, the chemical formula for CO. Molecules of CO goes on the diagonal, you're converting to moles. The number 1 goes next to moles. 6.02 times 10 to the 23rd goes with molecules because that's your things. This would be 7.3 second E24 divided by 6.02 second E23, and that will give you 12 moles of CO. Now, let's come down here and take a look at these practice problems. How many moles of argon do 1.81 times 10 to the 22nd atoms of argon represent? So you want to put atoms of argon on the diagonal and moles of argon on top. The number 1 goes next to moles. So that goes here, and then my atoms would have my 6.02 times 10 to the 23rd with it because those are my things. You're dividing 1.81 second E22 divided by 6.02 second E23 is going to give you 0.0301 moles of argon. 3 sig figs, 3 sig figs. For number 2, we have 2.25 times 10 to the 24th molecules of CO2. So molecules of CO2 will go on the diagonal. Moles of CO2 will go on top. The number 1 goes next to moles, and the 6.02 times 10 to the 23rd goes with my molecules. So this is 2.25 second E24 divided by 6.02 second E23. You're going to get 3.74 moles of CO2. Number 3, a 1 liter intravenous bag of saline contains 9.27 times 10 to the 22nd formula units of NaCl. How many moles of NaCl is in this? So that means your formula units are going to go on the diagonal, and we're going to moles, so that will go on top. You'll put the number 1 next to moles, and you'll put the 6.02 times 10 to the 23rd next to formula units. Here we are dividing 9.27 second E22 divided by 6.02 second E23. You're going to end up with 0.154 moles of sodium chloride. Okay, now we're on to molar mass. And the mass of a mole of an element's atoms is known as molar mass. We're just restating the definition of a mole. So the molar mass of an element is its atomic mass expressed in grams. So a mole is the number of atoms in 16 grams of oxygen. Restated, a mole of oxygen atoms weighs 16 grams. And the atomic masses on the periodic table on the back of your book give you the molar masses. That's grams per 1 mole of that substance. And the molecular mass or formula mass is the sum of the constituent atomic masses. So if I have water and I have 2 hydrogens, hydrogen is 1.01 on the back of your book on the periodic table, and I add that to 1 oxygen with 16.00, I'm going to get 18.02 for the mass of water. So a mole of water molecules consists of 1 mole of oxygen atoms and 2 moles of hydrogen atoms, and therefore it weighs 18.02 grams. Similarly, if I'm looking at sodium chloride, which is what they're showing you down here in this figure, here is your water over here, which we just discussed, one oxygen and 2 hydrogens. These are your atomic masses adding up to 18.02. If I'm looking at sodium chloride, a formula unit of sodium chloride is NaCl. That's just the simplest unit of the compound, the ionic compound. I have a mole of sodium ions and a mole of chlorine ions or chloride ions or chlorine atoms. The total mass is going to be 23 or 22.99 on the back of your book for sodium, 35.45 for your chlorine. I add them together. I'm going to get a mass of around 58.5 for a mole of sodium chloride. So the molar mass is simply the atomic mass expressed in grams, and the molar mass of a compound is its molecular or formula mass expressed in grams. They're all the same thing. And if you take a look at the next page, at these practice problems, we're going to be calculating the formula mass, also known as the molar mass, of different compounds. So here I've got nitrogen dioxide, which is NO2. On the back of your book, nitrogen is 14.01. I have 2 oxygen in this formula here, so 2 times 16 from the back of your book. And 46.01 is the atomic mass or the molar mass or the formula mass for NO2. What is the molar mass of Na2Cr2O7? I have 2 sodium, 2 chromium, and 7 oxygen. So 2 times sodium at 22.99 plus 2 chromium from the back of your book on that periodic table at 52 plus 7 oxygen at 16. This is 261.98 grams. Now, if they're asking me for the molar mass, that's the mass in a mole of that compound. What's the molar mass of iron 3 sulfide? Iron 3 sulfide is Fe2S3. So if you look at the periodic table on the back of your book, iron is 55.85. I have 3 sulfurs. Sulfur is 32.07. I get 207.91 grams per mole for that compound's molar mass. Now, we are using the molar mass as a conversion between grams and moles since its unit is grams per mole. So you know that you can write the equivalent statement, like a mole of water is 18.02 grams. You know that you could write that as 2 different ways, with the mole on the bottom or the mole on the top of the fraction. And we can use it, depending upon our needs, to convert between grams or moles. Let's come down here. Actually, before I do that, let me point out this little convenient conversion cue. Moles to grams, you're going to multiply by the molar mass in grams on top over 1 mole. Grams to moles, you're going to multiply 1 mole over the molar mass in grams on the bottom. So we're going to use that down here in these practice problems. What does 2.65 moles of table salt, which is NaCl, weigh? So that means they're asking me to convert to grams. So moles of sodium chloride is on the diagonal, so we can cancel it. Grams of sodium chloride was on top. Now, 1 mole is equal to the atomic mass or your formula mass in grams from the periodic table. So I put the number 1 next to moles. What goes here is from the periodic table. So if I look at the back of your book, sodium is 22.99, chlorine is 35.45. When I add these together, I get 58.44. So I multiply it across. 2.65 times 58.44, I get 155 grams of sodium chloride. That's the same 3 sig figs as I started. For number 2, 0.87 moles of NH3. I put moles of NH3 on the diagonal because I want these units to cancel. I'm going to grams of NH3. I put the number 1 next to moles here. The number that goes here is from the periodic table. Nitrogen is 14.01. And I have 3 hydrogens at 1.01. So that's going to give me 17.04. I multiplied 0.87 by 17.04 to give me 15 grams. That's 2 sig figs, which is the same as I started. Number 3, very large quantities of chemicals are produced in the chemical industry. Worldwide production of sulfuric acid is estimated to be around 2 trillion moles annually. So that means 2.0 times 10 to the 12 moles of sulfuric acid. How many tons of sulfuric acid is this? A ton is 1,000 kilograms. So we can remove the NE from the tons and just use TON if you'd like. Now, moles of H2SO4 needs to go on the diagonal because I need to cancel it. You know you can convert this to grams. The number 1 goes next to moles. The number that goes here for the H2SO4 grams is from the periodic table. 2 times 1.01 for your hydrogen, plus your sulfur has a mass of 32.07, plus 4 oxygens at 16. So this is going to be 98.09. These units cancel. And since this conversion goes to kilograms, I need to convert my grams here to kilograms. That's a 1-step metric conversion. The number 1 goes next to kilo, that's the prefix. 10 to the 3rd goes next to the 1-letter base unit. There I've canceled grams. Now I can convert kilograms to tons. Kilograms goes on this diagonal to cancel. Ton is on top. So the number 1 goes next to tons. The 1,000 or 10 to the 3rd goes next to kilograms. So this is 2.0 second E 12 times 98.09 divided by second E 3 divided by 1,000. You're going to get 2.0 times 10 to the 8th tons. That follows the 2 sig figs that I had in the very beginning because the power of 10 and the number 1 are exact. And we can go on to the last section on the next page. Now, up to this point, we've just been converting moles to grams. Here in this practice set, we're converting grams to moles. For number 1, it says that we have 62.2 grams of gold. We want to know how many moles of gold that is. Well, grams of gold needs to follow you onto the diagonal so you can cancel it, and then moles of gold will go on top. Remember, a mole is equal to the atomic mass or the molecular mass in grams from the periodic table. So the 1 goes next to moles. The number that goes here is from the back of your book on the periodic table. Gold is 196.97. 62.2 divided by 196.97 is 0.316 moles of gold. 3 sig figs is what I began with. That's why I end with it. Number 2, 3.88 grams of CO2. Grams of CO2 is on the diagonal, so I can cancel it. Moles of CO2 is on top. The number 1 goes next to moles. The number that goes next to CO2 is from the periodic table. Carbon is 12.01. I have 2 oxygens at 16 each. When I add that together, I get 44.01, and this is 0.0882 moles of CO2. 3 sig figs, 3 sig figs. Number 3, smelling salts are used to revive an unconscious athlete. A capsule of smelling salts contains 500 milligrams of ammonia carbonate. How many moles of ammonia carbonate is this? We need to convert milligrams to grams so that we can actually convert grams to moles at another step. The number 1 goes next to the prefix milli. 10 to the negative third goes next to the 1-letter base unit, grams. And then we can convert grams to moles of your ammonium carbonate. The number that goes here is from the periodic table. You get that from 2 times 14.01 for your nitrogen, plus 8 times 1.01 for your hydrogen, plus 12.01 for carbon, plus 3 oxygens at 16. So this comes out to be 96.11 for its molar mass. So 500 times second E, negative 3, divided by 96.11. I want 4 sig figs in my final answer. 5.202 times 10 to the negative third moles of ammonium carbonate.